This brief revision topic introduces the key points on Stokes flow. Now, Stokes flow is seen in a wide variety of different situations. You've got let's go back a slide. You've got very viscous flows. So, for example, here, this is the famous pitch drop experiment at the University of Queensland, where we've got this pitch, a derivative of tar, dropping from a funnel, and one drop comes down every decade or so. It's an incredibly viscous fluid. Here we've got a glacier. So these are very slow flows. It turns out ice flows just like a fluid if you work on long enough timescales. So here this glacier is flowing incredibly slowly, and also a lot of biological fluid mechanics involves Stokes flows because you have very small flows. And the thing that unifies all of these is that the Reynolds number is much less than 1. Remember, the Reynolds number is defined to be UL over nu, where nu is the kinematic viscosity. The dynamic viscosity mu is equal to rho, the density, times the kinematic. So just to remember which way around these things are, this is dynamic, this is kinematic. That fits. So when the Reynolds number is small, that occurs either in very slow flows when u is small, very small flows when L is small, the length scale, or very viscous flows when u is big. So how does that allow us to simplify our governing equations? Well, if we scale the Navier-Stokes equations, we let velocities scale like capital U, we let times scale like, well, a time is going to scale like a velocity, length divided by velocity, right? Because a velocity is a length per time, so u is L over t, t is L over u, and all of our derivatives grad are just going to scale like 1 on a length scale. Sorry, this should be minus grad p here. Okay, so how do these different terms in this equation scale? Well, this here scales like u squared over L, because it's u over t, which is just u squared over L. This here is also u squared over L. This term here, we don't quite know how pressure scales, so this is just going to scale like p over L, whereas this term here scales like mu u over L squared, and again we don't know how force scales. But let's consider the ratio of 1 to the left-hand side. So we'd have 1 over the left-hand side terms. This scales like mu u over L squared, all over rho u squared over L. If we simplify this down a bit, we get mu over rho u L. Okay, this is just going to be 1 over the Reynolds number. So if the Reynolds number is really small, 1 is much bigger than the left-hand side, and we end up with the so-called Stokes equation, which is just mu grad squared u minus grad p plus f equals 0. And this is lovely because this is linear. Remember, Navier-Stokes is not linear because of the advective term, u dot grad u term, but this is linear. And we'll see what that imposes later on. But these here are the Stokes equations. We have div u equals 0 just from incompressibility, and div sigma equals 0 just to derive that. If you remember that du by dt is equal to div rho du by dt is equal to div sigma plus body force, and if this term we have already argued is small, this is what our scaling argument here gave, so that gives the same result. Basically, it's saying that inertia is not important and everything is dominated by viscosity. Okay, so what are the implications of this linearity? Well, the equation is instantaneous, there's no time dependence, so a key corollary of instantaneity is something called the Scallop theorem, and it's why in really slow viscous flows you can't have you get nowhere if you make a reversible motion. So say you've got this microorganism that's just got 2 arms like this, and in order to swim, it pulls these arms out, and then once they're extended right out as far as they'll go, it pulls them back in exactly the reverse motion. Well, there's going to be no net change happens here. Nothing happens. Because of the lack of time dependence, this stroke has exactly the opposite effect to this stroke. So you don't swim anywhere. So microorganisms have to be really clever about how they're swimming if they're swimming in Stokes flows. Time reversibility. So that's where we get from time reversibility, instantaneity and time reversibility. Linearity and space reversibility leads to some really interesting cases. So let's just consider a wall here, a vertical wall, and we've got this sphere falling at some velocity in some direction under gravity. Now, we're linear both in the forcing, so both in F, the body force, and in the boundary conditions we apply. So this means that our velocity is proportional somehow to g, because g here is the forcing. So let's flip g. So we'll take g goes to minus g, and that means that u has got to go to minus u. So the physical setup now is we have this same sphere, u goes to minus u, g is now pointing upwards. Okay, we're also space reversible. So let's flip vertically. And we're space reversible because that's essentially like taking y goes to minus y, and these equations are linear, so that doesn't change anything material. So if we flip vertically, we come back to this case now. U is pointing like this and g is pointing back down. But, as we'll see later, solutions are unique to the Stokes equations given forcing and BCs. Now the forcing and BCs are exactly the same here as they were here. So this solution has to equal this solution. So we'll call this 1, this 2, and this 3. So u in 1 equals u in 3. That means that u can't have this horizontal component, it's just got to have a vertical component. So by mirror symmetry, spheres have to fall vertically under Stokes flow in this specific case. And this can be exploited in lots of more complicated situations, but this is another one of the surprising implications of linearity of the Stokes equations. There's a few more properties of the solutions of the body force free Stokes equations. So if we take the divergence of this equation, which we'll call star, we find that mu grad squared div u is equal to del squared p. Well, now div u is 0 because we're incompressible, so the pressure is always a harmonic function. If instead we take the curl of star, well, the curl of a gradient is 0, so we have mu grad squared, we can pull the curl inside the Laplacian, equals 0, and that just implies that the vorticity is a harmonic function in this case, or a harmonic vector. We can also take the Laplacian of the equation, and that gives us that mu grad squared u minus grad squared p, but remember grad squared p is 0 equals 0, so we just have grad to the 4u equals 0, i.e. u is a biharmonic function. Or vector field, perhaps is a better way of saying vector field. Yeah. So the solutions to Stokes' equations have a lot of very interesting properties which allow us, well, we've got equations that we can solve for these solutions, they're quite nice and linear, and so these are incredibly powerful when it comes to solving problems with Stokes flow systems. There's even more theorems involving Stokes flow. We'll start with this little lemma here, and I'll show you how to prove it. So if we've got a Stokes flow US and sigma s, this is our velocity field, this is our stress, and u being just some velocity field that is incompressible, then this identity holds. Now how do we show that? Well, the left-hand side is equal to 2 mu es, so everything with an s superscript is the Stokes flow solution. This is just equal to sigma s ij plus p delta ij, because remember, sigma ij is minus p delta ij plus 2 mu e ij. Lovely. If you're unsure about index notation, remember to go back and check that video out first. So this is the left-hand side. Now let's contract these indices, and we're left with sigma ij s e ij plus p e I dv. Now recall also that Eij is 1/2 dui by dxj plus duj by dxi. So Eii is just div u. Well, this is 0. So the left-hand side is just equal to sigma ij s Eij dv. Right, I'm going to use a slightly clever trick now to rewrite Eij. So Eij is equal to dui by dxj minus 1/2 dui by dxj minus duj by dxi. And it's important to note that this tensor here is anti-symmetric. If you switch the indices, you switch the sign. Okay, but remember, this is symmetric. The stress tensor is symmetric by definition. So if you contract an anti-symmetric tensor with a symmetric tensor, you get 0. Again, go back to the index notation video if you're unsure about that. So we're just left with the left-hand side equaling just the contraction of this symmetric tensor with this first part instead. So we have sigma ij s dui by dxj dv. Okay, then we'll rewrite this as a derivative, total derivative, d by dxj of sigma ij s ui dv minus the derivative of ui d sigma ij s by dxj dv, just using the product rule. But this here is div sigma I, which is equal to 0, because one of the equations of Stokes' flow is that the divergence of the stress tensor is 0. Therefore, this integral is 0, and we're left with just this integral. And then use the divergence theorem to turn this into a surface integral, and we just get dv sigma ij s ui nj ds, as we wanted. Now this might feel a little bit useless, but there's two key results that we can prove here. So, the first one is called the Reciprocal Theorem. And if we take us and u to be equal to u1 and u2, where u1 and u2 are both Stokes flows, then this equation here tells us that v 2 mu E1 ij E2 ij dv is equal to dv sigma 1 ij U2 ij, or U2i, sorry, nj ds. But if we instead take us and u to be U2, U1, and remember we can do this because both U2 and U1 are Stokes flows, we have 2 mu Eij2 Eij1, this is the same thing because they're symmetric, is equal to sigma ij2 ui2 1 nj ds dv. I'll just put here, for the purpose of people reading these notes, for u1, u2 Stokes flows. That means that because these integrals here are the same, we have dv sigma ij1 ui2 nj ds is equal to, remember this is not squared, this is a 2, sigma ij. Maybe it's better to write these with little brackets just to make it really clear that we're not taking powers here. Sorry for adding the time, but hopefully that gives you a little bit of time to take this in. There, ambiguity gone. And this is the reciprocal theorem. Okay, so that's incredibly helpful for solving a lot of problems. The other thing that we can show with this is uniqueness. So remember I said that Stokes flows are unique if we have the same BCs. And forcing. So let's assume not. And that U1 and U2 are distinct solutions that are different, that satisfy the same boundary conditions and are both Stokes flows. So let's let U star equal U1 minus U2. And U star is also a Stokes flow because of linearity. So if U1 and U2 are both Stokes flows, U star is a Stokes flow. And so let's apply this lemma with US U is equal to just U star, U star. Okay, so the left-hand side is 2 mu E star ij, E star ij. And this thing here is greater than or equal to 0 dv. So this whole left-hand side is greater than or equal to 0 is equal to dv sigma ij star u star I mj ds. But u star equals 0 on the boundary, because they have the same boundary conditions. So the velocity is the same on the boundary. So this equals 0. And the only way this can happen, therefore, is if E star is everywhere 0, because this is otherwise positive. So this implies the only way this can happen is if this difference is just a rigid body motion. But the values of u are the same on dv. So the rigid body motion has to be 0. So u star has to be 0. And therefore we've got uniqueness of any Stokes flow satisfying the same boundary conditions on the same domain. Okay, so that's a very small taste of some of the important points you'll need for Stokes flow. This will be really covered in a lot of detail in slow viscous flow, but if you want to read up more beforehand, here's some helpful sources.